Okay, so we're going to get into polar form of complex numbers, and what you have known complex numbers in this form is the rectangular form, and you can graph these rectangular forms on a complex plane, which is what this is. And the horizontal axis is the real axis, the vertical axis is the imaginary axis. So this point A plus BI is A on the real axis part, B on the imaginary axis part, and that's the point A plus BI. Z is a common variable used for a complex number. So if Z is used to represent this complex number x plus IY, that would mean that, and that's here on the complex plane, that would mean this is x on the real axis, y on the imaginary axis, and it would end at the point x, y. Okay, and that represents that complex number x plus IY. You can find if there's a vector that goes from the origin to that point, you can find the magnitude by the same thing that we've been doing, the square root of x squared plus y squared. This is also the modulus of that complex number. Okay, I don't need that extra a. So the modulus is the magnitude of a vertex that, or of a vector that goes from the origin to that complex number on the complex plane. Basically, to find the modulus, you do the same thing as when we found the magnitude. So in this one, to find the modulus, I have square root of -3 squared plus 2 squared. Now, pay attention that I didn't use the I. The I is not the vertical component of this vector. It's only the coefficient to the I, which was 2. So I have square root of 9 plus 4, which is the square root of 13. So the modulus is equal to square root of 13. So when we did sine, cosine, tangent, sine and cosine, sine was equal to y, cosine was equal to x. But we only used it with the unit circle. So the radius was always 1. Technically, the sine of an angle is the y divided by the radius of that circle. Cosine is x divided by the radius. And tangent is still y divided by x. So from that, we can get the polar form for what x and y is. The rectangular form of a complex number is what you're used to, x plus y times I. The polar form, I would take, to get the x, take this, multiply both sides by r, and x is equal to r times cosine theta. Y is equal to r times sine of theta. So that means z is going to be r times cosine theta plus r sine theta times I. And it can be written this way: r times cosine theta plus I sine theta. R is the modulus or the magnitude of that complex number. So here are some steps to plot, or I'm sorry, to change the forms from rectangular form to polar form. Okay. First, plot the complex number in a complex plane. Note the quadrant of it. That's the important part. Find the r by finding the modulus, and then find theta by using tangent of y over x. Some of these you're going to be using the calculator, some you won't need the calculator. And then you write it in the polar form. Once you have theta, once you have r, you can write it in the polar form. So here's an example. Okay, I first am going to graph it. And my real part is square root of 3, so that's going to be right about here. My imaginary part is -1, that's going to be right about here. So I have this complex number square root of 3, -1, and it appears in quadrant 4. So now I need to find r. So r is square root of square root of 3 squared plus -1 squared. So that's going to become the square root of 3 plus 1. R is equal to square root of 4, so r is equal to 2. And now I need to find theta. Well, tangent of theta is equal to y over x, so that's -1 divided by square root of 3. And this becomes negative square root of 3 over 3. So theta is equal to tangent inverse of negative square root of 3 over 3, which is going to be the pi's over 6, but because it's the fourth quadrant, theta is going to equal -11 pi over 6. So now I can write it in polar form, and that's going to be z is equal to 2. One second. Give myself some more room. Z is equal to 2 times cosine of 11 pi over 6 plus I sine 11 pi over 6 and that is the polar form of that complex number. I'm going to do this next example on the next page. Z is equal to -2 plus I. So I'm first going to graph it. And I have -2, +1, so it's in quadrant 2. So when I find r, that's going to be r equals the square root of -2 squared plus 1 squared. So r is equal to square root of 4 plus 1. R is equal to 5. Find theta. I'm just going to go straight to tangent inverse of 1 over -2 is equal to theta. Tangent inverse of -1/2. I'm going to have to do this one in the calculator, which theta comes out to -26.565. And understand that this is in quadrant 4 though. And remember, mine appears that this complex number appears in quadrant 2. So what I have to do is add that 180 degrees, and that will give me the angle of 153.4. So now I can write the polar form. Z is equal to the square root of 5. I didn't write that up here, but it was the square root of 5 times cosine of 153.4 plus I times sine of 153.4. If you want to put those in parentheses, you can. And that is the polar form of that complex number. So in this one, we're going to change to rectangular form. Okay, it's given to me in polar form. And because this first one is one that's on the unit circle, you won't have to use a calculator. Cosine of negative 120 is going to be past 90 by 30 degrees. So the x is negative 1/2. The y value of that, the sine of that, is going to be square root of 3 over 2, positive. And that's multiplied with 4. So when I distribute the 4, negative 4 over 2 plus 4 square root of 3 over 2i, and I can simplify this to become negative 2 plus 2 square root of 3i. I'm going to rewrite this 2i times the square root of 3. So the I doesn't look like it's in the radical. And so this one, because 109 is not in the unit circle, you can use the calculator for that. Cosine of 109 becomes negative 0.326 plus I times 0.946. And then when I distribute the 3, I get negative 0.98 plus 2.84 times I. And that's the rectangular form of the complex number. Okay, so this is the last set of notes, so I got a really good joke for you. Why do eggs not make good quarterbacks? Because when their defense cracks, they're way too quick to scramble. I cracked myself up like an egg.